Hello again and welcome to video lecture on operations research, and we are now in the notes linear programming with SPICE chapter 8. Chapter 8 was called Duality, and now we are in the second section called Duality Theorems, where we finally tell you what is what is the duality. So far we have considered very many different forms of LPs, and that was of course partly in preparation to understand what is the duality and why is it. And let's start with the relatively non-technical description, relatively, about the dual. So what is a dual? A dual of an LP, so linear program, linear optimization problem, is actually another LP that's constructed from the original LP, and then the original LP is in this business typically called the primal LP. And how is it constructed? So according to the following rules or ideas. So we start an LP that's a primal, and we want to construct an LP that's a dual, and now this is another LP, it's different LP, it's not the same as the primal, in a different form. In any case, so these are the rules. So the objective is inversed. So a maximum in the primal becomes a minimum in the dual, and vice versa. So that's somehow simple. But then things become more complicated. So the decision variables in the primal, so what we can decide, become actually the constraints in the dual. So what we can decide in primal will be the things that constrain us in the dual. So something completely different. And yes, this is a kind of a opposite thing or companion thing going on here. How about the constraints in the primal? So what constraint us in the primal will be what we can decide in the dual. All right. And then upper bounds are turned into lower bounds and vice versa. So these go the kind of simple way, the opposite direction. The technology matrix is actually transposed. So if you think about the tabular representation you have for an LP, then you transpose everything. So rows becomes columns and vice versa. And finally, just to emphasize, the sign constraints are kept. We like sign constraints. So if they are not there, then that's the exception to the rule. So here, this is the kind of rules or ideas how this goes more precisely. So let's look at formally what this means. So if the primal LP is given in the what I call now the primal standard form, so this is the standard form A20, it's a maximization with upper bounds like this, then its dual LP is in, again, let's call it the dual standard form, the follows. So let's see how this here turns into this. So maximization turns to minimization, okay. Here I use Z just to denote the solution of the maximum, so since that's used there, let's use something else for the minimum, and usually then it's denoted by W. Alright, here we had C transpose X. Now we actually have here B transpose Y. So now this Y is, since the X's I use decision variables here, since these are different, I use Y for them. And so here we had the C. Now here we have the B that's coming here. Okay. What about the constraints then? So here we had AX here we have a transpose, A transpose Y. And here we had an upper bound, here we have a lower bound, but the lower bounds are not the B's. So the B's here are the constraint turned to somehow related to decision variables. So instead we take this C here. So A prime or A transpose Y is greater than or equal to C. And sign constraints are kept. So if we have an LP, any LP, we can turn into primal form like this, or the primal standard form, and from this we can construct the dual standard form, which is this. Alright, so let's have an example to see how this goes. And the example 8.22. We are given a following type of LP, and yeah, this is just an example, nothing. There is no story behind this. I just figure out an LP that is actually not in a standard form, so we have to do a little bit work here. So the point or the motivation is to find the dual of this LP. And since this LP is not in standard form, we don't have it's difficult to see what its dual is. If you are familiar with duality and are clever enough, you can probably change this, figure out the dual of this, or some form of the dual of from this of this LP directly. I'm not clever enough. So that's the point. So before constructing the dual, we will actually transform this into standard form. This is not necessary, you don't have to do it. Sometimes you can be clever and find the dual first without transforming into a primal standard form. But okay, at least I don't feel very clever, at least not now. So we turn this first into a standard form. So there was algorithm 8.10 to do this. We could follow that here step by step, and indeed this is something you should do on your own. So actually now is a good time for you to stop the video, take piece of paper and a pen, look at the algorithm 8.10. So go to the notes here and start going through these steps. Step 1, step 2, step 3, step 4, whenever needed. And yes, take this LP here and make a standard form out of it. I'm serious, do it now. Okay, welcome back. I hope that you now have transformed this into a standard form, and I hope that you got this. If not, then either you or me or both have made a mistake. So this is in standard form now. It should be, so it's a maximization of minus that. That's obvious, that happened. So this lower bound had to be transformed to upper bound, so it's minus this is less than equal to minus this. It's here. This is as it is. Nothing happened there. And then this equality turned into two inequalities. So this thing here is less than equal to 1, and minus this thing here is less than equal to minus 1. And the sign constraints, these we had there already for all, so that's nice. So the step 4 where we had to split things into positive and negative part, we didn't need that. Okay, so here we have a standard form. So how do we then transform this into its dual? So let's see if I can, maybe I make this slightly smaller. It will be probably hard for my eyes, but you have good eyes, I hope. But this way we can have, let's make it still smaller. So I want to have this primal and dual forms there visible. And can I have them? Still not. Now everything should be visible, if not clearly, at least visible. So this is the primal standard form in general, and in this example this is now in the primal standard form. C is here, B is here, A is here, everything is upper bound, and we have sign constraints. So what is the dual standard form then? And the dual of this. So we have a minus z, so let's call this minus w then, to keep the minuses here to correspond that here we started with minimization and plus sign. So it's a minimization w equals b transpose something. So what's the b now? So this is the standard forms. The b will be minus 11, 111, 1 and minus 1. And this will correspond to the decision variables y, and we will have 4 y's because we have 1, 2, 3, 4 constraints here. So the objective is to minimize minus w minus 11 y1 plus 111 y2 plus y3 minus y4. That's it. Alright, what then? Then we will have upper bounds and C here. So these are the upper bounds. And what is the C? C is now, of course, here it's minus 50, minus 20, minus 30. Like this. Okay. And then the final part, the part where it's easy to make a mistake, is to look at the technology matrix here. So it will be the technology matrix in the primal standard form, but transposed so that rows turns into columns. How do you do it? Something like this, vice versa. So let us look at it here. What happens? So again, we are not looking at this, we are looking at equivalent standard form LP here. So the first row here is minus 2, minus 3, minus 4, and this should become the first column in the dual. So minus 2, minus 3, minus 4. So this minus 2 corresponds to this minus 3 corresponds to this, and this minus 4 corresponds to this minus 4 here. Okay. Then the second column here comes from the second row here. So 12, 13, 14. So this is the 12, 13, 14 here. So the third row here is 1, 1, 1. Yes. So it becomes the third column here. So 1, 1, 1. And the final constraint is minus 1, minus 1. Minus 1, so it becomes here minus 1, minus 1, minus 1. And we then have to just remember that there are sign constraints for these variables, or dual variables if you like. So this was an example how to do the dual transformation. So how do you construct a dual out of the primal? So usually if the primal is given in a non-standard form, it is a good idea to transform it into a standard form. So then we have something like this. And from the standard form, it's then relatively straightforward to construct the dual. Max goes to min. Objective will come from the constraints, and the constraints will come from the objective. Upper bounds turn into lower bounds, and yeah, A is transposed. So rows and columns are transposed. So that was just a way to make it. Okay, I should point out maybe a small thing that is unnecessary, but maybe important to note here that we actually started with a primal that's a minimization and turned it into a maximization, and then figured out its dual to be a minimization. There's nothing wrong with here. This was correct. On the other hand, if you think about the idea here, that is, how do you relate primal and dual? So primal is a maximization, then dual is a minimization. So of course it would make sense to have that if the primal is a minimization, then the dual is a maximization. Indeed, it would be more natural. So maybe this was not so natural what we did here. And indeed, since the primal was a minimization, maybe this dual, especially since we have a minus sign here, to make it a maximization might be a more natural. And also, okay, this is now presented in a dual standard form, which kind of makes sense or is natural to minimization. But since we started with minimization, the primal, maybe it isn't the dual, maybe it might be reasonable to change it into a maximization and actually not present the dual in a dual standard form, but a primal standard form. I'm sorry, this may look confusing, but the idea here is that, okay, dual LP is an LP, and you can again represent any LP in different kind of standard and non-standard forms. So let's just present this in a standard form. It's pretty close to a standard form. It's easy to do it, and somehow it seems natural. So there's a minimization of minus W, so that would be then a maximization of minus W, which is just a maximization of W. And what about here? We have lower bounds and we have negative signs here. So if we just multiply everything here by -1, these become upper bounds and there are minuses, so the negative signs actually disappear. So this here can be written like this. Okay. And now it kind of, I think this fits better to the whole picture. So if we started with an LP, which we call primal, which is the minimization of something, it's not completely in standard form, but or the dual standard form would probably be more natural for the minimization. In any case, this LP here, which can be written also in this form, so this and this LP, they are the same. This can be transformed in the dual like this way, but this is also a way to represent its dual. So this here, this maximization, is the dual of this minimization. Okay, then a small remark for the end of this lecture. I hope you are not too confused, and this is kind of to clarify a thing. So here we have 4 LPs in principle. This, and this. Okay. This LP here is the same as this LP because this is just this in a primal standard form. So when we look at different equivalent forms, we are not changing the LP. The LP is the same, meaning that its solution is the same. It describes the same problem. Maybe it's just written in a different way, but the problem is the same. And the solution is obviously then the same. But what happened here was the dual transformation. So this LP here is not the same as this LP. So the primal and dual are not the same. They are different LPs. So the solutions are different. But they are very closely related. We shall see this soon. Okay. And finally, of course, this LP is the same as this. So in this example, we have two different LPs, the primal and the dual. And we have two different representations for the primal and also for the dual. This is something to keep in mind. Okay, see you in further lectures later. Bye.